Welcome to the second video on finding eigenvalues and eigenvectors. Just as an overview of what we've seen so far, we have a 2x2 linear system of differential equations. We converted that over to matrix form. All right, and we've seen that finding straight line solutions is an important concept that led us to the idea and the notion of eigenvalues and eigenvectors. So if we can find, this is kind of our first case that we're going to resolve, where we have distinct eigenvalues. So if we can find two eigenvalues of the matrix A of coefficients, and I'm just going to write that over on here. Remember, this matrix of coefficients A is either written with rounded parentheses around the matrix or square brackets around the matrix. All right, it's just the coefficients of the x and y in the first row, coefficients of x and y in the second right-hand side of our system in the second row. All right, if we can find two distinct eigenvalues of that matrix, then there will be two corresponding two corresponding eigenvectors, one to lambda 1, one to lambda 2, and those ones will actually turn out to be linearly independent, and therefore we can build a general solution. So here's the steps we're going to be taking, and we're going to be focusing on mainly just first step 1 and 2 in the video, where we're finding the eigenvalues and eigenvectors, and then writing down the general solution. Right. Other recordings will talk about enforcing the initial conditions, which is not super difficult. Step 1 and 2 are the main steps. So first thing we're going to do, find all the eigenvalues associated with the matrix A. Then if we have two distinct eigenvalues, we're also going to try to find those two distinct associated eigenvectors to those eigenvalues. Then we can form a general solution. All right, and let's just say a little bit more about what that general solution looks like. All right, in particular, what is y1 going to be? Well, it's not going to be, if we have distinct eigenvalues to our matrix, real distinct eigenvalues, then we're going to have a constant k1, and then we've seen before that it's going to be a scalar multiple of the eigenvector v1, and that scalar function of t turns out to be e to the lambda 1 t. And likewise for the second term, we're going to have k2 times e to the lambda 2t times v2. All right, so we've got even more explicit information about how the general solution is going to look. It's going to be our function y1 of t, which is e to the lambda 1 t times our eigenvector v1. Okay, so just going to clean that up a little bit, and then the second term, right, is going to likewise be a constant, arbitrary constant, times e to the lambda 2 times lambda 2t, and then times the vector v2, the fixed vector v2. All right, so let's get some more practice on finding eigenvalues and eigenvectors. All right, so the next example we're going to look at is this one here. And remember from our prior recording that when we find the eigenvalues, the steps to doing that is, 1, we're going to write down the matrix A minus lambda times the identity matrix. And then step 2, we're going to take the determinant of that matrix, A minus lambda times the identity, and set that equal to 0 and solve that equation. And solving that will give us the eigenvalues. That equation that we get is going to be a quadratic equation. It's referred to as the characteristic equation. Okay, so let's put that into place for this example. So it's going to be A minus lambda times the identity. All right, so we write our matrix out. I'm just going to use rounded parentheses around the matrices. A little simpler to write that. All right, now when we do lambda times the identity matrix, remember the identity matrix is the matrix we get by putting 1 down the main diagonals and 0s in the off diagonal. Well, if we multiply all of those entries by lambda, multiplying 0 by lambda doesn't change it, but multiplying 1 by lambda gives us lambda down the main diagonals. All right, so what do we end up getting with this matrix? We always just do the same thing, which is you're going to subtract lambda from the main diagonal entries, and then you're just going to leave the off the main diagonal entries alone. Okay, so that's the first thing to do. Then we write down its determinant. Which is going to be always leading us to a certain quadratic expression. So write down that determinant, and remember how we do the determinants. I'll just quick put it in, and then we will erase this shading. So we're going to multiply down the main diagonal, subtract the product of the off diagonal. Alright, so then it's going to be minus 2 times 1. Okay, so just multiply that out. What we end up getting here is 12, and then what, plus 4 lambda plus 3 lambda, distributing each term to each term, and then plus lambda squared, and then minus 2. Alright, now my suggestion would be to rewrite this in descending order. That's the way we're more used to solving quadratic equations, because we're eventually going to set that equal to 0. So we're at lambda squared plus 7 lambda plus 10. Okay, so set that equal to 0 then and solve it. Alright, and that will give us our eigenvalues. So lambda squared plus 7 lambda plus 10, and put that equals 0. And again, however you want to solve it doesn't matter, but you're either going to solve it by factoring or the quadratic formula, or if you want to, you could solve it by completing the square. Alright, most people are probably going to take the factoring approach, right? So we'd have 2 and 5 multiply to 10 and add up to 7. Again, we set each factor equals 0. I'm going to skip that step and just write it out. What's that going to give us? We're going to get negative 5 and negative 2 are the solutions to the characteristic equation. So those are the two eigenvalues here. Okay, from there, what do? We're going to label these. I like to label the smaller one lambda 1. And then we're going to label the other one lambda 2, the larger one lambda 2, lambda sub 2. Then we've got to, for each one of those eigenvalues, we're going to find an associated non-zero eigenvector to the matrix. Okay, so we'll start out with lambda 1, which is negative 5. We want to say, okay, we need to find some associated non-zero eigenvector v1, which we don't know right now, so we're just going to call it a generic xy, and we're going to use the eigenvector condition that a times that vector is got to equal lambda. A times the vector v1 has got to equal lambda times the lambda 1 times the vector v1. Okay, and then we're going to put in here the matrix and put in there the eigenvalue, which is negative 5, and then we're putting an xy for v1. Again, generic vector. We're going to now figure out what our matrix was. If we forget, just go back to what we were. What was our matrix again? It was 4, 1, 2, negative 3. Okay, so now we need to express that out. All right, and just do that matrix multiplication on the left-hand side. Now remember, when we do that matrix multiplication, it's the first row times this column. That'll be our first row in the product, and then it'll be second row times that column vector. All right, so we're going to get negative 4x plus 4y, and then 2x minus 3y on the left side. Distributing the scalar through, we multiply each component of that matrix by negative 5, so negative 5x, negative 5y. Okay, now just setting each component equal to each other, we're going to get then what? Negative 4x plus y is equal to negative 5x, and then 2x minus 3y equals negative 5y. Okay, just a quick comment on that, just to save you a little bit of time. After you do that a number of times, after you do that several times over, you're going to realize what the left-hand side comes out to every time. And let's just kind of highlight that. Notice these numbers here in the matrix, negative 4 and 1, are the coefficients of x and y. All right, get rid of that now. And vice versa, the numbers in the matrix 2 and negative 3 are the coefficients of x and y on the left-hand side. All right, and then on the right-hand side of our system, we have our eigenvalue negative 5 times both x and y. All right, now this system of two equations and two unknowns is what we refer to as an overdetermined system. All right, but it's a system that's going to have lots and lots of solutions, lots and lots of non-zero solutions, and we just need to find one. All right, so we got to find one non-zero eigenvector, one non-zero pair of numbers x and y, which is going to be components of our eigenvector that satisfy that. All right, so I'm just going to solve the first equation for y by adding 4x to both sides, and that's going to give me y is equal to negative x. All right, likewise with the second equation, if we added 3y to both sides, The second equation would tell us 2x is equal negative 2y, which again, if we solved it for y, could solve it for x or for y, we would get y equals negative x again. So these things lead to the same equation, and that's what I mentioned a minute ago when we said it's an overdetermined system. There's going to be lots of possible solutions, ordered pairs x's and y's, that'll make this work. We just got to find one, and we got to find one non-zero pair. So at this point, a lot of times what we're going to do is just let x or y or whatever be something convenient. It's going to be convenient for us to let x equal, let's just say 1. You don't have to choose 1. You could choose 2 or 3 or negative 1. Whatever you want, really. The only number you can't use is 0 here, because then we would get both x and y to be 0. And we're looking for a non-zero eigenvector. Well, if x is 1, then y comes out to negative 1. So the eigenvector v1 we were looking for, again, it was this vector which we were trying to determine. Now we have determined it. It is 1, negative 1. Okay, and that means our first straight line solution, y1, is going to be e to the lambda 1, which is negative 5t, times v1, which we just figured out to be 1, negative 1. Okay, we got to do the same thing with the other eigen value, is find the corresponding eigenvector. All right, so we'll repeat those steps, and it'll be a little bit different to find the other eigenvector associated to lambda 2, which was negative 2. All right, just pause here for a second just to mention, though, I chose x to be positive 1. If you make a different choice, it's okay. You'll just have a different looking general solution. Okay, let's go on to the next one. All right, so what was lambda 2? Lambda 2 was negative 2. So we're going to do the same thing again. We want to find a vector v2, which we don't know yet, so we're going to call it a generic vector x and y. Okay, and we want to use this condition that a times v2 is got to equal lambda 2, which is negative 2 times v2. Now I'm just going to go straight at this, and you can pause it and write it out if you need to, but the steps would be exactly the same as what we did before. We would get the coefficients of our matrix, right? Negative 4 and then plus 1, or x plus 1y is going to equal, that's our first left-hand side, and then 2x minus 3y is going to equal our second component on the right side. Well, what are we doing? We're just taking the vector xy and multiplying it by negative 2, so we're going to have negative 2x in the first equation, or first component, and negative 2y in the second component. Setting components on the left and right hand sides equal gives us this system of two equations, two unknowns. So once again, we get two equations here. All right, that system of equations has lots and lots of possible solutions, x and y. We just have to find one non-zero one. Okay, so now rewriting this, I'm just going to, in the first equation, let's add 4x to both sides. And if we do that, we would get y is equal to 2x. Okay. Likewise, with the second equation, if we just added 3y to both sides, we would get 2x on the left and 1y or y on the right. Once again, we're seeing we get this exact same equation in each case. That doesn't happen, as we'll see in our next example, all the time, but it does for this particular example that we're looking at. Okay, so what are we going to do? We want to find, right, there's lots of solutions to this equation, y equals 2x. There's a whole line of solutions if we think about it in the xy plane. We want to find any one except 0, 0. All right, so we'll just take the easy approach here. Let's just let x equal 1. That tells us y is equal 2. All right, there's your component to the eigenvector v2. So v2 is the vector 1, 2. All right, there we go. Now, what is the corresponding solution y2 then? For finding a straight line solution, it's e to the lambda 2t times v2, where v2 is the vector, the eigenvector, or a eigenvector, we should say more correctly. Well, what do we get? We get e to the negative 2t times 1, 2. Okay, let's write the general solution out, and then maybe we'll do another example in this video, all right, to wrap this up. Okay, so what is the general solution going to be? All right, when we have distinct eigenvalues, the general solution is going to be a scalar multiple of your first straight line solution plus another scalar multiple of your second straight line solution. And now let's just put the formulas in that we found. We get k1 times e to the negative 5t times our eigenvector, and if we went back up, we would find that that would be 1, negative 1, plus k2 times the vector we just found, which was e to the negative, or the solution we just found, e to the negative 2t times the vector 1, 2. Okay. So I think what I'm going to do is pause the video here, or stop the video here, and then on the next one we'll do another example.